Okay, so good morning to all of you once again. So now we are all almost okay. One more lecture is pending after today's lecture of the semester. Now I think I'm going to cover another topic. Okay, that is on severe plastic deformation. Then the last lecture on Friday that will be on intermetallics, plastic deformation of intermetallics. Okay, so and the pending thing, I think quiz 3 marks are pending. Okay, so by this weekend, Sunday, you'll get those marks. Okay, then assignment marks, you'll get it. Okay, by next Wednesday. That means before okay your term paper presentation and Vios exam starts. So that basically starting on 11th, 12th, and 15th we have okay term paper presentation and Vios examinations. Okay, so before that you will be knowing okay your okay marks for the internal 50 marks. Okay, and the final basically I'm considering term paper report, presentation, and Vios. All okay these three together for 50 marks. Okay, so you'll be getting the all together your performance you'll be knowing okay by 18th of this month you'll be knowing your okay performance of in the course. Okay, is it clear?
Yes, sir.
Okay,
Yes, sir.
fine. Yeah, I'm sorry because that quiz 3 marks have been delayed. Evaluation has been delayed because of so many okay classes. Every day I'm having some. Okay, so now I think I wanted to complete the teaching part. Then I'll okay sit on that evaluation procedure. Okay, evaluation of the quiz 3 and assignments. Okay, so I think anything else you want to have clarification about the term pair presentation, Vios exams, anything else? Is it clear to all of you?
Yes, sir.
Okay, fine, good. Okay, basically, I think in my previous lecture, basically what I had discussion about the dynamic deformation activities which are going to take place at elevated temperatures, at high temperatures, okay, greater than greater than 0.4, 0.5 times the melting point, and the test temperature is okay, is about okay about
Sir, there
0.5.
is sir disturbance coming from your end.
1 minute, just. How about now? Hello, is the noise still persist?
A little,
Hello.
sir. A little noise is there.
Oh no, where it is coming from?
Sir, I think it's because of the earphone placement, sir.
Earphone placement. Okay. So I hope is it okay better now? Or
Yes, sir.
still no, same noise is coming.
It is better now, sir.
Okay, fine. So previous lecture basically we had discussion about okay dynamic deformation activities. Okay, especially there we discussed about restoration processes. The microstructure can get okay can get recovered, can undergo recrystallization. That basically restores the strain-free grains. Okay, so there are two processes which can happen during deformation itself. Okay, especially when you deform at high temperatures. Those are called dynamic recovery and dynamic recrystallization. Okay, so dynamic recovery basically related to annihilation of okay opposite sign dislocations. If they can happen during deformation, that can lead to formation of subgrains. Subgrain structure is going to develop. But okay, that has been explained by method called polygonization mechanism. By mechanism, polygonization mechanism, where dislocations of opposite sign common together on the same plane can get annihilated each other. So that can lead to formation of a subgrade structure. So when that's a typical characteristic, okay, curves typically we see stress strain curves. typically we do see work hardening curve will be like this, that we already had enough discussion about work hardening. In case of recovery, dynamic recovery, what we see, the stress strain curve is going to be like a okay, steady state kind of stress, saturated kind of stress we do see. So there basically work hardening and dynamic recovery together is going to take place, that can balance together. In that case we do see stress is going to be constant. In case of drx, if the drx is happening, in that case what happens, the stress strain curve typically initially will have a peak followed by a drop in stress, then again becomes a steady stress. Okay, so this is a kind of a typical kind of curve what we see, materials which undergoing okay dynamic recrystallization. You have to remember that there are three different types of dynamic recrystallization. One is actually continuous dynamic recrystallization, and second one is a discontinuous dynamic recrystallization. There's another thing called geometric okay dynamic recrystallization. Okay, there are three different types of dynamic recrystallizations. This kind of curve what we are seeing can be seen only when there is a discontinuous dynamic recrystallization. When there is a continuous recrystallization, which is nothing but a extended recovery, that means recovery, we are going to see subgrain formation, and those subgrains can evolve into a actual grains. When you say actual grains, means the grains should have a boundaries of a high angle boundary character. Okay, that means the misorientation angle should be greater than 15 degrees. Then only say the grain, actual grain of a material. So subgrains basically which will have a low angle boundary character. So that's what I think. Continuous dynamic recrystallization will not have a that can hump and followed by decrease and steady kind of strength. Typically, we do see like a recovery kind of dynamic recovery kind of work hardening plus dynamic recovery can be seen, and it is basically balance of work hardening plus dynamic recovery. That this kind of recrystallization or continuous dynamic recrystallization can happen when these low angle boundaries, subgrains having a subgrains with a low angle boundaries, can convert into a high angle grain boundaries. So high angle grain boundaries can be found by homogeneous increase of misorientation. Slowly, the misorientation is going to increase when you deform more and more. Okay. At the same time, we may see some places progressive lattice rotation. Okay, around the boundaries, we do see some rotation can take place that can also lead to formation of a high angle grain boundaries. And another thing, some micro shear bands. Okay, those can also people have shown around the micro shear bands. We may see formation of a high angle grain boundary grains. Okay, so we had this discussion about continuous dynamic recrystallization. Then we discussed about discontinuous dynamic recrystallization. Typically, whenever we do say discontinuous dynamic recrystallization, we do see this is a kind of characteristic curve. It can be like a simple hump or a multiple fluctuations in a stress strain curve can be seen.
Sir,
Yes,
sir, in the last two slide,
yes,
in y-axis we are saying stress, but that stress is also true stress only, right?
yes. These are all
Okay,
true strain plots.
fine, thank you.
These are true strain plots. Okay, so then
Hello,
we
sir.
had discussed. Yes,
Sir, DRV happens at a lower temperature than that of DRX, right?
it's not necessary to be okay. It's depends depending on stacking fault energy of material. Okay, depending on stacking fault energy of material. So we do see in a high stacking fault materials, we do see dynamic recovery is going to happen first. Okay. So what we are talking about is static recovery, static recrystallization. Typically, we do see static recovery first at low temperature, then followed by when you go to a little bit high temperature, we do see a static recrystallization. Here, when you say dynamic recovery, dynamic recrystallization, okay, so dynamic recovery usually happens, when there is a high stacking fault energy, where you see recovery happens first. Okay, that means we don't have any boundaries, any energy driving force for recrystallization to happen. Okay, so that's where actually the difference basically comes from a stacking fault energy. And also people also see here, it's not like the high temperature low temperature kind of thing. Typically we need to have a high temperature, whether it's a drv or drx, we need to have a high temperature. Okay, but which material is going to undergo recovery, which material is undergoing recrystallization, basically depends on a stacking fault energy.
Sir, so typically if TRX happens like typically at a higher temperature than DRV, I mean both of them are high temperature only, but DRX happens at a much at a slightly higher temperature than DRV, then in the first graph the DRX curve should be lower, right? Because if temperature
No,
is
no,
more,
this is
flow stress
no.
should be less.
We are talking about this one. Okay, this is a schematic thing. Okay, it is not material. Okay, we didn't talk about what materials here.
Okay,
Schematic.
okay,
Okay, it's
okay.
just schematic cause. Okay,
All right,
it's not
all
for
right.
any particular material because a particular material will not show both of them. Okay, all of them. If you take aluminum will not show all these things. Okay, we'll show okay either this work hardening initially followed by okay this thing we may see this one directly. We do not see this thing. It's a
Okay,
material
okay.
dependent. Okay,
It's
it's
just the
nothing. No,
characteristic you're
there's
showing
no
here.
there are no okay numbers here. Okay, it's just
Okay,
a y-axis is a plot. Okay, whether you take this curve, stress versus strain. Okay, this particular curve will be stress versus. That's it. Nothing to do with your stress here.
okay, okay, sir.
The
Understood.
magnitudes are not given here. That's why that was this is schematic representation of okay typical okay stress strain curves what we see flow curves what we see is the material exhibiting only work hardening is the material exhibiting work hardening plus DRX the work hardening plus recovery. Okay. Is it clear?
Yes, sir. Clear.
Okay. Yeah. So in case of DDRX, okay, typically, okay, one characteristic feature what you see, how stress strain curves will be like this, and microstructurally, okay, formation of okay, this necklace kind of structure is going to form. Strain-free grains are going to form along the boundaries of the okay deformed grains. Okay, so this necklace structure, whenever we see at the onset of okay, when the moment onset of recrystallization take place, there is some onset okay strain. Okay, that strain we do see recrystallization going to happen. If you stop and look at the microstructure, we do see formation of this necklace kind of structure, strain-free grains along the boundaries of a deformed grain structure. Okay, so this is a kind of okay characteristic way of okay saying that the material is undergoing discontinuous dynamic recrystallization. Okay, so then we had discussion about typically there are okay three different types of mechanisms people use for okay saying the how the recrystallization is taking place in a material. Okay, it can be static or dynamic. Okay, or it can be when you say dynamic, it can be CDRX or okay DDRX. So whatever there are three different types of mechanisms of well-known mechanisms. There are several mechanisms. The well-known mechanisms are actually we had discussion about subgrain formation followed by a subgrain okay boundary migration. So this migration is a boundary migration. The other mechanism subgrain rotation and coalescence and strain induced boundary migration. Okay, so most of the times when there is a DDRX, okay, we do see SABM is a common mechanism. Okay, SABM is a common mechanism which explains formation of a okay recrystallization in a material during deformation itself. So I think we had enough discussion about all these things. I hope are there any doubts here? I think now let's move before moving to next topic. So any doubts, please let me know. Are there any doubts? Is it clear? So, I hope I'm online.
Yes, sir.
Okay, yeah. Okay, this is a whole story about a dynamic deformation activities at elevated temperatures. So today's okay topic is on a severe plastic deformation. Okay, I hope some of you might be knowing because during masters or okay PH bachelor's days you might have heard about severe plastic deformation. Okay. What is speciality? Okay, when do you say the deformation is a severe plastic deformation? Any idea what I think I wanted to know how much you already know. Okay, some of you. Okay.
Yes, sir. Strain
Have
rate
you
is
heard?
very high when we deform the
Strain rate
material.
is okay. Strain rate is not necessarily very high. Okay, it's not necessarily very high.
Okay.
When do you say the okay the plastic deformation is a severe plastic deformation? No, no idea. Or you have heard any names severe plastic under severe plastic deformation? What are different methods available?
Equi-channel angular pressing.
Yes. Okay. Any more?
Friction state processing.
Friction stir processing. Okay. Any more?
Torsional pressing or something like that.
Okay. It's called high pressure torsion. Yes. Okay. Okay.
Even sir, machining per se can also be called severe plastic deformation.
No, that's where I think, okay, that's where you have to remember that, okay, the actual definition of a severe plastic deformation, okay, it indicates that, okay, we should induce very large strains. Okay, the true strain values can be 4 or 8. Okay, true strain of, okay, can go very high, large, okay, true strain values, and it should have some hydrostatic component. Okay, at the same time, the specimen, the sample what you have taken before deformation and after deformation, it should have same dimensionality, same shape. There should not be any change in shape, but it should have a induced large amount of strain, okay, under some hydrostatic component. Okay, that is what I think people have defined severe plastic deformation. Okay, in case of machining, you cannot retain the same shape. Okay, we do induce severe, okay, strain. Okay, we do induce very large amount of strain in the material while machining, but that's not a severe plastic deformation. So the definition, okay, this is what, okay, any method or metal form under extensive hydrostatic pressure that may be imposed a very high strain, not a strain rate, okay, high strain on a bulk solid without the introduction of any significant change in the overall dimension of sample, and having the ability to produce grain refinement. Okay, so this is basically defined as a severe plastic deformation. Is it clear? The kind of, okay, definition we should, okay, induce, we should able to induce very large amount of strains that should not lead to any change in shape. A dimension should be retained, okay, before and after deformation. At the same time, the intention of severe plastic basically to refine the grain size. Okay, that means that method should have the ability to refine the grain size. That method is called severe plastic deformation. Okay, so there are, okay, so many methods have been, okay, developed from 1997 onwards. Okay, it's I think relatively new, but in 1997 onwards, okay, so I think 92 also they started 92 a little bit, but yeah, 97 onwards there's huge, okay, research has gone into understanding, developing various severe plastic deformation methods. Okay, some important methods. Okay, basically the techniques which involve severe plastic deformation. Okay, one actually based on equal channel angular pressing. ECAP is the, okay, I think foremost important thing. It's not the first one, but actually important technique which come under category of a severe plastic deformation. There are, okay, n number of variants. Okay, in the equal channel angular pressing, there are so many variants have come. People have developed different stress states. Okay, but the most important is the equal channel angular pressing. The other one, techniques based on using a torsion shear, okay, under high pressure, okay, HPT, high pressure torsion, and techniques based on pressing and forging, okay, multi-directional forging, and there are techniques based on rolling, accumulate roll bonding, okay, and corrugation and straightening method. Okay, so this is another method, and there are also people use combined techniques. Some of the things can be combined, can also, there are methods which having a combined techniques. So most important things I will discuss: ECAP, high pressure torsion, okay, ARB and RCS and MDF. Okay, these methods will be discussed, and what is the mechanism, how the grain refinement is taking place in the material. So I think these things will be discussed in, okay, today's lecture. Is it clear? I think just about the definition of a severe plastic deformation.
Hello, sir. Sir, I was
Yes.
thinking no strain, I mean, high strain without any shape change. I mean, how is that possible? Because
Yeah, that's
strain,
where,
okay.
okay, that's what the techniques. Okay, if you look at the techniques, we'll understand. Okay,
So,
so if you
so
look at
it's
ECAP, yeah, if you look at ECAP here,
okay.
okay, it will have a die, okay, some cavity, okay, cavity will be, can be a L shape or some angular, okay, can be there. Typically the first one what people have developed, okay, this kind of, okay, L shape kind of die. We place the material here, take a cylindrical specimen or like a cuboid specimen, okay, cuboid specimen, and if you apply force with a plunger, what happens, it comes out. Okay, this is the inlet die channel, and this is actually outlet channel. So the material comes, okay, the dimensions, okay, here the dimensions are same here, okay, inlet and exit and okay, entry dimension, exit dimensions are same. The cross section is same. When you press the material is going to undergo okay deformation and comes out with a similar shape. Okay, so this is called equal channel. Okay, these both channels are of equal. Okay, in terms of a cross sectional area, if it's take the same. Okay, only there are some okay people use okay there's a phi angle and psi angle. Okay, so depending on these angles, the amount of strain induced in the material is going to vary slightly. Okay, depending on this angle, how much angle you are giving, okay, phi and psi. Accordingly, the strain induced into the material is going to be changed. Here, we are actually compressing the material within a channel that basically induces some hydrostatic component. Okay, and we are also deforming material with some force onto the material. Okay, so and it is the material is undergoing okay a kind of shape here internally it's going in shape change, but externally we do see same shape at the end. So if you take any plane, okay, that plane is undergoing a shear deformation. We do see a significant shear deformation. If you take any represented volume of material, that material under that volume of material undergoes a shear deformation by having this kind of setup. Okay, I said depending on these angles, the strain, the total strain, okay, in a single pass, like one pass, okay, is estimated using this. Okay, for example, n is a one pass. Okay, depending on number of passes, how many times you are doing it. Okay, that basically number of passes and angle by using this angle. Okay, so by depending on the shape of the okay die angles, phi and psi, we'll get a strain value. Okay. So typically around zero 0.9 to 1, okay, true strain value of 0.9 to 1 can be induced in a single pass. In a single pass, I can induce a true strain value of 1 by having this kind of setup. Okay. So within this equal channel angular pressing, okay, there are 4 different variants. Okay, there are 4 different methods. I can say there are 4 different methods within a equal channel angular pressing. Okay, so depending on how you are pressing the second time, the second pass, because one pass you have taken a cylindrical specimen and pressed it, and you got a cylindrical specimen. Again, when you want to okay do second time, okay, because there's not much shape change, then again when you can put it again, you can deform it. Okay, so the second pass, how we are doing it, okay, so that makes a difference in the method. Okay, for example, here the root A, okay, there are kind of root A, root B, BA, root BC, and root C. There are 4 basic processing routes available in ECAP okay method. One, okay, if I take specimen and if I load it directly,
Sir,
that is hello.
sir, I mean, in this particular process, how are we calculating strain actually?
It's a strain only by just using a okay, design of the die dimension. Okay.
No, I mean, strain is like, we say final dimension by initial. So how exactly, I'm not able to visualize the strain value because shape is same.
Yes.
So how, and is it like the shear kind of thing is happening?
Yes, this shear. So it's a shear component. Okay. The
So whether
shearing.
the strain will be the last in the shape, this, some tilt is there. I mean, how exactly we calculate?
No,
If we
no, it's not
quantify,
tilt. This is not tilt. Okay. This we do not just only based on the die design only how much strain is getting induced into the specimen.
but when we
Okay.
say strain is 0.9, what does this mean actually?
So internally, if you take a particular plane, we'll come to that. Okay, a particular plane, how it basically deforms. Okay. So locally, we do see okay the material is going to okay, each shear plane. We have crystallographic planes. Crystal. Okay, if you take a cubic element, okay, the cubic element is going to undergo that much strain. It's a shear. Okay, the shear strain will
Okay.
be converted into effective true strain. Okay,
Okay.
you are basically taking a true strain. If you take a particular plane, how it changes when it okay, from here to here. Okay, around at this angle. Okay, we do see a kind of shear activity. So that shear component is used to calculate shear strain, a particular representative cubic element in undergoes. Okay.
Okay. Yeah.
It is no angle. Basically, this is shown only, but it's you will get only okay cross section, same cross section. You get okay, just shaded. That's it. You stop it here. But what it says, if you take any plane, okay, it undergoes okay a kind of shear activity at this junction. So that shear strain in the material is used and calculate the effective, okay, true strain, okay, in the material. Okay.
Okay, sir.
So the root A is basically you take the specimen and put it again, second pass. Okay. Again, third pass also like that. Okay, we do. So that's called root A. And root B, okay, root C, let's come to root C. Root C, what we do, we rotate the sample to 180 degrees. We rotate the sample to 180 degrees and put it, okay, in the die second time. Okay. Then in third time also, third pass, what then again rotate it to 180 degrees. Okay, so like that is called root C. Okay, in case of root BA and root BC, it's basically in BA we do rotate the sample one time 90 degrees clockwise direction. The second time, the second third pass, we rotate it to anti-clockwise direction 90 degrees. Okay, that's called root BA. In case of root BC, what do we do for each pass? We rotate it 90 degrees, okay, in a same direction. In a same direction. Okay, so after 4 passes, it becomes again comes back to original position. Okay, so this is what, okay, kind of root BC. Okay, so these are actually very important, okay, steps people are, okay, used to, okay, get, okay, microstructural refinement, the grain refinement in the material. Okay, is it clear about this different routes under recap? Any doubts?
Sir, so in all the routes, we are starting with the horizontal position of the bar itself.
No, horizontal. No, we put it here. Okay, we get the bar, this specimen. Then we
Okay.
just simply place it. Okay, that specimen will be placed second time in the
Okay,
same
okay.
die.
So after the plunging action, it comes out of the other end. Okay.
Yes, this is okay. We send the material comes out, okay, from this channel. It's open. There is open. Okay, opening will be here. The material come out of this die. Then second time when you put it in die, what is the variant we are using? We are putting directly. Then it's called root A. Okay, in root C, we rotate it to 180 degrees. The specimen will be rotated to 180 degrees, then placed in a die. So in root B and root BC, basically give 90 degrees rotation. But in root BA, we do give clockwise, anti-clockwise rotation for each, between each pass. Okay. In BC, we do see one particular direction, we do rotate the specimen 90 degrees. Okay. Every pass, we'll have see 90 degrees rotation. We are basically what we are doing cross loading. Okay. What we are doing cross loading the specimen. Okay. We are changing the loading conditions, okay, onto the specimen. If I say equal channel angular pressing, typically, okay, we do talk about shear deformation. We do talk about shear deformation. There are two different types of shears we do see: pure shear or simple shear. Or you can also see mixed intermediate shear also will be seen. What is the difference between pure shear and simple shear? Any idea? Both are same or different?
In pure shear, sample will dimension will change, sir.
Dimension will change.
And
Okay. But in the simple shear, we do not see such dimension change. If you take a cubic element, okay, have you heard? I think these two are different terms at first same term.
both are different, sir.
Both are different. Okay. Okay, this is the difference. If I take a cubic element or square element, okay, if there is a pure shear, okay, there will be a, okay, what we are seeing a shearing activity, but at the same time we do see distortion, okay, in both directions, x and y directions. Okay, if we take alpha and beta direction, we do see distortion in both the directions. Whereas in case of simple shear, we do see the shear activity happens, okay, only in one direction. We don't see this rotation, okay, component in a simple shear. So in most of these SPD processes, especially ECAP, if we take ECAP process, okay, we are basically inducing simple shear. Okay, if you take a particular plane in the material, okay, if you take a particular plane, so now you see have a cubic element, take it for simplicity, take a cubic, okay, bar. and if I press it, okay, we are going to see this kind of shear activity. It is basically simple shear. Most of the times, the material undergoing simple shear. Okay, so if you take different planes, okay, x, y, z planes, okay, how the cubic element undergoes deformation in a single pass, in a single pass. Okay, so a particular element is going to undergo, okay, like this deformation. Okay, so this is in a single pass. When you go to second pass, okay, or third pass and fourth pass, okay, depending on the variant what you're using, depending on root, ABC roots, A, B, A, B, C, and C roots. Okay, for each pass, that particular cube element, how it undergoes, okay, shape change, okay, is like this. We take a root, okay, A, root A, okay, we take X, Y, Z, one of the, okay, planes. If I take initial, I'm taking everything A, okay, square cross section. Okay, how it changes its shape change. Look at here. The particular square, okay, shape is going to change for each pass, and it also going to depend on, okay, what route you are using it. Okay, so this is the initial, and then after first pass we'll have like this, second pass will be like this, third pass will be like this, fourth pass will be like this. Again, look at here the BC. Okay, if you take a BC route, okay, after every fourth pass, okay, the fourth pass, okay, we are going to have a similar kind of shape. What does it mean? If I take a equiaxed grain, okay. So again, after, okay, if 90 degrees, 90 degrees rotation, okay, we are going to get again equiaxed, but the size is going to be smaller. Okay, so the grain within this cubic element, if you have a grains, those grains are going to be finer in the shape. Okay, so these are the shearing characteristic of a particular plane. If you take a plane, how it is going to change. Okay, that basically depends on, okay, how many number of passes are giving and what type of route you used, ECAP route. Accordingly, we do see the shearing characteristic going to be different. Okay, so simple shear is the most dominating, okay, activity that take place in most of this SPD process. Okay, especially in equal channel is very well known. Okay, a particular cubic element can undergo, okay, simple shear activity. Okay, so if I take a material aluminum,
Hello, sir.
yes, yeah,
Sir, in the previous slide, there is a shape change, right? Like even in simple shear, there is a shape change. So we were saying
no,
there is no change in shape.
no, no. Finally, you get, okay, your bulk material volume will be, shape will be same. You don't get shape change here. Okay, your bulk volume will get same shape. Locally, we do see, okay. So that means basically what I want to say, whatever cross section you are getting, you will get same cross section again. Okay, but there will be
Okay.
small. Okay, there will be some extra material come, initial material. There will be some initial cone will be there that will be cut, trimmed off. Okay, we will see. Okay, that because of this, depending on root, we may see. Okay, the shape we may get some okay, protruded thing. If you trim that protruded portion next up, okay, you'll get again same circular cross section.
So we do that process.
Yeah, yeah, we need
Uh,
to do between each passes. We need to trim that. Okay,
okay.
the ends. You need to trim the ends. The trims will have, okay, the ends. Okay, both ends will have some shape change. But the moment we cut the trims, okay, the ends, okay, we'll get the same shape again.
Okay. Okay. So plunging plus the trimming action is called equi-channel angular pressing, right, sir?
Equal channel
E-
angular
e-
pressing basically means,
Equal.
okay, equal channel. This one channel, okay, and this okay, another channel. Okay, this is called both of them having a same cross section. Okay, that's what that is called equal channel angular pressing. Okay,
Right.
we are using a plunger to apply load onto the specimen. When apply load onto the specimen, okay, the material has to flow. We are having some hydrostatic component. Okay, we are holding the material. So when you apply force, what happens locally? Okay, every plane undergoes a shear activity. Because of shear activity, the first portion and the end portions will have a some kind of slanting depending on what route you are using. So if you trim those end parts, we'll get again same cross section area of the specimen. We may lose small amount of materials, okay, in this process. when you do e cap.
So the shape could change, but the volume isn't. Sorry, the shape will not change, but the volume can change
No, 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 volume also will not change. There's no defect. Okay, no defects
because,
will be
sir,
developed. Okay,
because you're trimming off the material, right?
that is your volume. You are cutting. We are losing the material. The ends we are losing the material. Okay.
So there'll be change in
And-
the mass also,
no,
right?
no. Because people also do without trimming. Also they put it. That also can do it. Okay. Without trimming also can put it when you press it. Again. Okay. It gets pressed up. Okay. So people actually are better. Okay. Because what happens many times that material can get stuck. Okay. So that's why what they do trim the things. Otherwise you don't need to trim. You can put back that again. Okay. When you put it again, it will going to get pressed, compressed. So trimming is not mandatory, but it is suggested to trim it because that may avoid the clogging in the channels.
Sir, but
Okay.
if there is no trimming, then shape is going to get changed, right? At the end, like as you
No,
said,
no, it will change
there's
again.
going to be
What
this
they do?
extra material that will come.
No, that when you put it again, it gets pressed up. The bottom part of the okay, this thing gets compressed.
Okay,
Okay, then undergoes again. Okay, so trimming is not mandatory step. It is a
okay,
optional thing.
okay.
Okay,
I
but
still didn't understand how the density isn't going to change because if
density,
there is trimming, there'll be mass change, right?
yeah, density. We are losing material. Okay, is what you say. We are going to lose the material. The density of material is going to be same.
Okay. So
Okay, you're
So
okay,
what
whatever
so
we are losing, that
along with the mass, there'll be also some volume change maybe.
volume
So
change if you trim
density
it.
will be constant. Okay,
Yeah, this is constant.
okay, okay.
sir, application of strain will be different in both edges. I mean, side side and five side edges.
No, no, the strain, actual strain taking place at this interjunction, okay, of the two channels.
Then what is the need
We-
of changing I mean, sample rotate? Why we are rotating
yeah,
sample?
we'll come to that. Okay, we'll come to that. Why? Okay, this is why. Okay, we are changing. Okay, we are giving a cross loading. We are creating some vortex metal flow. The metal flow is basically changing. Okay, every time. Okay, if you look at if I do not do, if I take a simple rolling operation, if you take a material, if you deformed 60 aluminum material, if you deform 68%, 90%, 97, 99%, typically what happens, we do get a elongated grains. Okay, we may see some subgrain structure, but still, okay, if you deform in one direction uniaxially, okay, under rolling, we do get a elongated grains. Okay, if I the same thing, if I use a E cap, okay, what happened? There is a shearing activity happening. Okay, the grains are undergoing shearing activity in a single pass. Okay, two pass, third pass, fourth pass. What happened? What is the difference between these two? Because this one is a rolling, other one is a cap. Look at the microstructure development. Okay, the microstructure is basically we are going to have a less. Okay, it's almost whatever seeing elongated grain structure is not be there. We are seeing a like again, we are seeing a equiaxed microstructure as much as possible. Okay, that basically what we are doing. Once you put it here, that's okay. After fourth pass in the root A, okay, if we took a root A, after fourth pass, we'll get a almost equiaxed grain structure. And also initially started with a coarse grain, okay, about 100 micrometers, whatever. Now it became a fine grain. Here we do see a lot of elongated shear bands, so many okay, deformation bands are going to exist in a deformed microstructure, in the elongated microstructure, in a in uniaxial deformation. Here we are shearing and okay, in a shearing because of shearing activity, we are okay refining the grain size of a material. Okay, sorry, yeah. Any doubts here? When you rotate it, okay, when you rotate it, okay, what happens? You can develop okay equiax microstructure much earlier because we are creating so much vortex. Metal flow is going to undergo a vortex every time you're changing the direction. Okay, so that can lead to much finer grain size. If you take BC root or BA root, okay, those two roots can give you okay much finer grain size even for the same number of cycles, okay, same number of passes. So
So basically, all the from metallurgical processing of the material, we get through casting or rolling, forging, whatever we do. At the end of the day, we need a desired microstructure, which is what do you call it, without any texture as such. In that process, we are using this what do you call it strategy to make sure we are getting EQX microstructure. That is the whole sole purpose, right?
EQX microstructure, and also because we won't get such a fine grains. Okay, here we get a very fine grains. We do not get such a fine grains.
But in rolling also there are so many ways now, sir, with different direction. One, I mean, rolling also passes. They do in different direction to create maybe similar microstructure. But we are saying this particular ECA is better or efficient process, right?
No, not efficient. Okay, there's a different efficiency is different term. Okay, connotation. When I say equal channel pressing, okay, you are going to get equivalent microstructure, no doubt in that. Okay, but that depends on number of passes. In a single pass, we do get almost okay similar elongated microstructure, but one is in the shearing different. Okay, the shear direction. Okay, in the shearing direction, we do see shear bands and all of them going to form. In the rolling, we are going to see like this. So if I want to, okay, if I want to get a equivalent microstructure after rolling, what should I do?
I mean, we have to what do you call it? Change the our we rotate in different direction. Maybe change the
Okay,
materials.
that means every time how to do, okay, that
Yes.
cross rolling, those things how to do, okay.
Yes.
Here, okay, it is happening internally, okay. Here, the
Mhm.
shearing happening, so that can lead to a fine grain size.
So, got it.
Okay,
And the
here,
second,
here there is a shape change.
I got it.
Look at
So,
here.
yeah.
If you take a rolling, okay,
Yeah.
we are taking with some, okay, 40 mm. Okay, after 99%, that means I have to go to point, okay, 4.4 mm, something like that. Okay, so there is we are reducing the shape of the thing. Here, there is no shape change. We get same shape almost. Okay, but at the same time, we are inducing a grain refinement in the material.
Okay. So one more thing, sir. I mean, last some slide you said that hydrostatic part of the material is what is giving this vortex flow. Is it so?
No, 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 not
No.
hydrostatic component. Hydrostatic component can reduce your okay defects, okay, concentration. When you induce very large amount of strains, there's a lot of defects can generate. Okay, void, so many voids can create. Okay, so many other defects. Okay, under
But,
hydrostatic component. Okay, we'll come to that. Okay, there is a slide, two slides. What are the basic rules of okay grain refinement by SPD process?
but as such, we don't get much what do you call it dislocation density increase in this
It
process.
increases. It increases. It increases a lot. It's a strain because we are shearing the component. Okay, locally we do induce a lot of dislocation. That's where
Okay.
the mechanism of grain refinement comes. Okay, so I'll discuss about the grain refinement. It's very simple. Okay, how the mechanism basically with dislocation generation with increasing strain, dislocations are going to get generated. Okay, I'll come to that. Okay, we connect it to the mechanism. Okay, how the grain refinement is taking place. Here, just I'm talking about eco channel pressing. Okay, how the grain. Okay, just grain refinement is going to be shown. It's going to be developed when you okay press the material in this shape. Okay, so this is the same material, just we have demonstrated. Okay, if I do rolling, if I do okay equichannel angle pressing, also how the microstructure is going to okay, develop. Okay, so coming to the next one, okay, methods. Just I'm talking about all methods. Next one is a HPT, high pressure torsion. This was the first, I think, oldest. Okay, high pressure torsion was very oldest. Okay, Bridgman was the first one who has okay mentioned. Okay, you can apply torsion and apply some compression both. Okay, so the torsion can give some kind of change in microstructure. That was a thing long back 1930 something like that. That time it was demonstrated by Bridgman. So, but around okay when this ECAP thing started coming, that people started okay look came okay started working on this high pressure torsion and see okay how the material is going to undergo okay what kind of microstructure change is going to take place, how the grain refinement is taking place. So it basically it's a torsion. We already okay if you look at the torsion, we are applying a torque to the material. So for example here there are two different types of setups. Okay, we can have a okay a cavity like okay there are okay supporting an anvil and place the specimen here and rotate it and with some compressive force, and rotate it and place the specimen here on surface. When it give twist okay torsion, okay, what happens, it is going to develop a shear strain. Okay, the torque, when you apply a torque to the specimen, so there is a twist. So that twist can lead to a developing a shear strain in the material. Okay, there's like two variants. Okay, the one is a closed one. Okay, other one is like a one opened one kind of. Okay, these are different setups, but both of them can induce torsion and along with some compression force. Okay, here when you take the specimen, typically people take some disc shape. Okay, some okay, typically some 10 mm, 2 mm, okay, kind of thick specimens. When you deform it, okay, under torsion and with some compression force, okay, there won't be any change in shape of the disc because the disc is constrained within a cavity. Constrained within a cavity. We are simply applying, okay, force, stress, shear stress to the specimen by torque and compression force. So all of us might be knowing, okay, how to determine shear strain and equivalent strain. Okay, if you disc, okay, if you have a disc, if you apply torsion, okay, the shear strain, this is basically r theta by h. Okay, theta is basically depends on the rotation, how much rotation you have given. Okay, so the number of, okay, 2 pi n, okay, number of rotations. Okay, so that basically gives you twist angle and the shear strain r radius of, okay, at any given location. Okay, r, okay, r is the theta, h is the thickness or height of the specimen, height of the specimen. The equivalent strain can be obtained from a true, okay, from the shear strain gamma by root 3. Okay, so when you deform a material under torsion, okay, your strain is going to vary from center to surface of the disc or periphery of the disc. Am I right? When you apply a twist, okay, to the specimen with some compressive force and twist, what happens? Because some strain is going to build up. Okay, the shear strain is going to be, okay, initially it is going to be once if you give one small tilt, a small twist, okay, the torque to the specimen, okay, the theta, okay, is this twist angle, we are going to give some twist angle depending on rotation, okay, number of rotation. So the r is basically tells that, okay, at any given location, okay, at a given across along this diameter of the, or okay, along the radius of the disc, the strain is going to be varied initially at a, okay, low strain. Okay, we do see, okay, there is a significant variation. Okay, where do you get high strain? In the disc, when you apply a torque to the disc, at the center or at the periphery of the disc?
Periphery.
Periphery. Okay, because the gamma is equal r theta by h for a given twist, for a given twist, okay, at the same size of the thickness, okay, with increasing, okay, okay, we think basically along, if you go from here to towards, okay, edge of the disc, your strain is going to increase. Okay, you need to apply so many, okay, turns. You have to apply so many turns, then only you can get a almost, okay, as much as uniform strain as possible. But still, okay, the major problem with this method, okay, still there will be some non-uniformity in the strain, okay, from center to surface of the, okay, disc. So one needs to apply more and more strain, more and more turns. That can lead to, okay, increased, okay, homogeneity, okay, from center to surface of the disc. Okay, so typically, okay, so people use, okay, this kind of formula because we are applying, okay, compression force and everything. So this is a kind of, okay, most, okay, only if you use only torque, it's a kind of equation is used. But when you apply compression force and everything, so the actual true strain is calculated, okay, under high pressure torsion equipment by using this formula. Okay, so we know that, okay, 2 pi nrh, okay, basically theta rh is basically shear strain. If I take, okay, effect of turns, effect of number of turns, okay, on, okay, shear strain, how much shear strain is getting accumulated, how much shear strain is getting accumulated. If I take, okay, disc and center of the disc 0, okay, and move, okay, towards left or towards right or towards left, okay, that means towards edge. If you take, okay, this is about 8 mm disc, okay, 8 mm, 8 millimeter diameter disc if I take. So from center, okay, so if depending on number of turns, okay, if you give one third turn or half turn, okay, 1 ton, look at here how the strain is getting accumulated. On the side edges of the disc will be having, okay, higher strain, and once you go to, okay, towards center, the strain is actually going to be lower up to 1 ton. Okay, so with increasing turn, basically we are seeing an increased accumulated strain at the edge, and also we are seeing the accumulated strain is going to be more, okay, increased basically with increasing number of turns. Okay, beyond 1 ton, okay, if you go for 2 turns or 3 turns, okay, we do see, okay, the accumulated strain is going to be as close, okay, okay, it's going to be higher, no doubt in that. The strain, shear strain is going to be increased with number of turns, and we do see some kind of reduced, okay, intensity, okay, change in the accumulated strain between the center to surface. Okay, nevertheless we do see, okay, we do see, okay, some gradient in the strain from, okay, center to surface of the disc under high pressure torsion conditions. Okay, if I take, okay, a 1 ton sample, okay, you take aluminum, okay, after 1 ton under pressure of 1.25 GPa, okay, the microstructure, okay, is going to be, okay, different. This is a, okay, left hand side and right hand side. Okay, one is actually in the center, other one is the edge. Okay, so we do see differences in the, okay, microstructure development, because, okay, your shear strain, okay, is different. Accumulated strain at the edge is different than the center. So that means actually, because of differences in the strain, accumulated shear strain, okay, that can lead to heterogeneity in the microstructure, okay, from edge to, okay, center of the disc. Okay, so one has to apply more and more turns so that we can minimize this heterogeneity. We can minimize this heterogeneity as much as possible. So higher turns are required. We can get a fine, okay, we are refining grain size, okay, we are getting very fine grain size, but we need to apply very high, okay, turns. That means high turns means higher the turns, higher the accumulated strain. So we need to give a high accumulated strain. So at low strains, typically at low strains, if we take two different types of materials, low stacking faulted material and high stacking faulted material. Okay, at low strains means we are talking about, okay, at this initial below 1 turns. Okay, so typically hardness is going to vary like this, because hardness, okay, if we take a disc, okay, specimen, okay, from center, okay, materials with fast recovery rate, which basically aluminum, okay, high stacking faulted materials, okay, will have, okay, relatively higher hardness at the center, okay, as compared to the edge. Materials which undergo, okay, slow recovery rate, okay, typically we do see this kind of change in hardness. Okay, because see, we are talking about a, when there is a recovery, that means your strength is going to come down. Okay, that's what happening. Okay, when you have more deformation at the edge, more deformation at the edge, okay, so that basically can lead to easy recovery. So that basically your hardness of the material at the edge is going to be, okay, lower than the at the center. However, after certain more number of turns, okay, more, if you give more and more strain, okay, we'll get a, okay, same, okay, hardness in the material. Okay, so this is the kind of effect of stacking fault energy. Okay, how the, okay, microstructure is going to develop, what is going to develop is going to depend on stacking fault energy material. Okay, if the high stacking fault material, if we take where the recovery can take place very fast, okay, so that basically can lead to a, okay, initially low hardness than the center, that original, as compared to original, okay, hardness of the material. Okay, so with more and more strain, we can get a, okay, we can get a almost, okay, same, okay, strain, a same hardness of the material. Okay, provided we are giving a more accumulated shear strain into the material. So is it clear about the high pressure torsion? Any doubts here? Am I online? I guess, I guess I'm
Yes.
online. Okay. Is it clear about high pressure torsion? Okay, we need to apply torque and compressive force together, and the specimen has to be in a constraint. It has to be constrained, okay, so that okay the material basically, even if you do not have constraint, okay, but the specimen will not undergo any deformation. Okay, we are applying compression at the same time giving it turn, okay, so that can lead to okay strain in the material. We are inducing a shear strain in the material without shape change of the original material what you have taken. Okay, any doubts here? Is it clear about high project origin?
Yes, sir.
So yeah, the next one, okay, rolling based thing. Okay, one is actually accumulative roll bonding. Okay, here, okay, they use simple rolling mill. Take the specimen. Okay, take the specimen first to roll. Okay, roll it to certain thickness. Okay, and cut it into two parts. Again, okay, bond. Okay, degrease the thing and okay, make it to two parts. Okay, again stack it. So this is how basically, okay, we are be subjecting the material, okay, to very large amount of strains. Here, what we are taking initially, we take a same material into two halves and deform it, okay, such a way that okay we can get a 50% reduction. Okay, then again take it, cut it into two halves, then put it to back into two okay sandwich, basically not sandwich, stacking together, then the stacked one again subjected to rolling. So this is like a cycle. Okay, so this is by this method also we can actually induce fine grain size material. Okay, provided okay it should have a good bonding characteristics at the interface. We should have a good bonding interface. Okay, if the bonding is not proper, then whatever exercise we do is going to be okay waste. So one has to okay we cannot do all types of materials which can establish bonding okay very easily okay under rolling conditions. Okay, so that actually we need to prepare a specimen. Surface is very important. The faying surfaces, okay, both the surface of the okay the stacked layer should be properly okay treated, then only we can get a good bonding by roll bonding. Okay, so by using a roll bonding technique and accumulate it, okay, what we are doing, we deform it and cut it into deform it to 50% reduction, give 50% reduction. After 50% reduction, again cut it to two parts, again stack it. Okay, this is a kind of cycle. For each cycle, okay, we can determine for each number of okay cycles, number of cycles. Okay, so we can get a what is the effective strain involved. Basically, we are talking about a reduction in the thickness, reduction in the thickness. Okay. There's another thing, repetitive corrugation and straightening. Repetitive corrugation straightening is called RCS. Here, okay, what it does, we take a okay sheet or plate, okay, typical sheets. Most of the time people do only sheets, and we have a kind of this kind of shaped roll, okay, shaped roll. So when you deform material, okay, so sorry, yeah, when you deform material, okay, we are going to subject it to like this, okay, with the two types of groups, with and with group, without groups. We take with and without groups and deform it, okay, in this fashion. Okay, so this is called corrugation, create a corrugation. So repeated okay corrugation we do and straightening. So, okay, so this is a kind of technique which is useful, okay, where we are not changing the shape of the sheet after end of the cycle, one cycle. Okay, this is together is called one cycle. Okay, is it clear about this repetitive corrugation straightening method and accumulate roll bonding?
Hello, sir. Sir, in the
Yes.
rolling, how much accuracy can we expect at the completion of the process? Like, you'll get the exact shape, like as it was, or there'll be
Yes,
some
yes,
change.
yeah, we'll get it exact shape. You have to give okay control this setting, okay, the set limit. 50% reduction,
Okay.
you have to give 50% reduction. Okay, now you have, for example, you have started with the 10 mm, okay, stacked one, you have to deform to 5 mm. Okay, so make sure that okay, we will get a equal, okay, only one direction only is changing, only length only changing, there is no change in width. That means plane strain condition, give a plane strain condition, Okay, most of the rolling operations, okay, can induce plane strain condition. Once you give plane strain condition, actually whatever change in, okay, thickness translate into a length. Okay,
Yes,
you are
sir.
reducing 50%, then cut it in 2 hours, then put them back again. Okay, two parts again, deform it. So we are basically subjecting the material, okay, under rolling conditions. Only thing we are just making is stacking. That's why it's called accumulative roll bonding. Okay, several times you have to do. So that can give fine grain size, okay, in the material. Any other doubts? It's a simple mechanical way of, okay, doing this repetitive corrugation basically. Okay, take a sheet and do under make it is a kind of shape. Then again press it, make it a straight. Okay, so this is basically the corrugation method step and the straightening step. Together is called repetitive corrugation. We have to do several times. That can lead to a, okay, fine grain size in the material. So is it clear about this important, okay, step, okay, the important methods come under category of SPD? ECAP we had discussion, HPT, okay, then we had discussion about ARB and RCS. Another thing, okay, based on forging, okay, by using a simple forging equipment, okay, you can also have a kind of method called multi-directional forging. Multi-directional forging. We take a specimen, okay, cubic specimen if we take, okay, so we deform it, okay, height, okay, make sure that, okay, you have 10 mm, 10 mm, 15 mm. When you deform it in one pass, what you are doing, okay, 10 mm sample, okay, now we are reducing 15 mm becoming a 10 mm. Okay, that is translating into, okay, in the dimension, okay, we are having some kind of constraint in one direction. So, so that whatever is deforming it, that can actually undergo, okay, translation into another dimension. Okay, other dimension will be remain constant. We have to apply some constraint in other direction, okay, using a forge close kind of forging step. Again, rotate it 90 degrees. Again, press it. Okay, that's called second pass. Again, okay, we put it. So this is how actually they do. Okay, people do. Okay, kind of using a multi-direction, changing the direction. Okay, every time, so that we can get a same shape again at the end. Okay, it requires a lot of accurate. Okay, it's not so accurate. Okay, because this is actually we need to have a proper die which can constrain the flow in one direction and translate one deformation, one direction, okay, deformation to another direction. It has to happen, okay, properly. It is similar to what you're seeing rolling also, okay. Here also what you're doing, we're using a forging equipment and deform it, okay, under compression and translate, okay, rotate it again, deform it, so like that. So finally we should get, make sure that the dimension, the shape change, not shape, the dimension change is going to take place properly at each pass. Okay, so it's basically it's a simple compression. Okay, by having a compression we are inducing a large amount of strain in the material, so that basically can lead to when you rotate it every time, so that basically changing the path of the deformation, so it can lead to a, okay, locally the microstructure, internally the microstructure going to undergo such a metal flow. Okay, when you have changed the metal flow in all directions, that can lead to a fine grain size in the material. Okay, so there are various methods are available, because I think now people have developed, I think almost more than 100 methods are available under SPD technique. The most important things what I discussed actually, ECAP, HPT, okay, accumulated roll bonding, RCS, and MDF, okay, multidirectional forging. If I talk about the mechanism, okay, how the grain size is refining, okay, the earlier, okay, thing, easiest thing what people have given explanation, okay, we do see when you deform material to very large strains, okay, there is a cell structure is going to develop. Okay, cell structure is going to get build up in the material, in a deformed material. There's a lot of dislocations going to generate and going to get, okay, rearranged in the form of a cell structure. Okay, when you deform more and more, okay, what happens, there is, you may see some kind of, okay, dynamic recovery even at low temperatures. Okay, opposite sign dislocations again get annihilated each other, can form a, okay, a kind of subgrains, okay, and, okay, subgrains are going to form, and these subgrains can become a high angle grain boundary grains with more and more dislocation, okay, when it under goes into the material. So it's basically depends. We are talking about SPD, this is deforming material, plastically deformed material to very large strains. When you deform large strains, there is a saturation of a cell size, okay, and that cells, whatever cells are formed, can undergo rearrangement. The dislocation can get rearranged, okay, so that can lead to a formation of subgrains, and these subgrains can become a full-fledged grain with a high angle grain boundary character when you have more and more deformation in the material. The same thing has been just given in different picture schematic way of we do develop a lot of dislocations during deformation with more and deformation. We do see formation of a cell structure, and this cell formation can lead to convert into a subgrain formation, okay. So these subgrains, with more dislocations, we do see all formation of a very fine grain structure, okay. So there is a first dislocation generation has to take place, and those have to be rearranged in the form of cells, and this cell structure convert into subgrains, and these subgrains are going to get reoriented, okay, with further deformation can lead to a formation of a ultra fine grain structure, okay. This is one of the established mechanisms for grain refinement during SPD process. So there is another thing people also given, okay, geometric dynamic recrystallization. Geometric dynamic recrystallization is another way of people have explained, okay, how the fine grain size is going to develop with a high angle grain boundary character, with a high angle grain boundary character. If I take, okay, this is a schematic thing, okay. Now, okay, we have, okay, these are assume these are my prior grains, the prior grain boundary, prior grain boundaries, these okay dark lines. Within that, okay, subgrains have been formed, okay, subgrains have been formed. When you deform to very large strains, you deform to very large strains, okay, that means what happens, okay, we are going to reduce the this kind of thing, okay, and we do see internally, okay, the cell size, okay, look at here, when you compress it more and more, okay, so we do see the prior grains which are of high angle character are there still. At the same time, okay, we are seeing a the size of this grain now, okay, subgrain close to 1 to 2 times of subgrain, okay, and having a high angle grain boundary character. Okay, here, okay, in order to explain this thing, but this is actually there is a shape change here. The shape change has taken place from here to here. That means, in case of this is applicable only when there is a shape change, significant shape change. Okay, so that was initial GDRX. That was a kind of debate happening, okay, about the GDRX, geometric dynamic recursion. Even people use this thing to explain what was grain refinement taking place in the SPD process also. So basically, so the actual mechanism basically people have so far valid explanation people used development of a cell structure followed by a subgrain structure and reorientation of a subgrains to a fine grain structure which is having a high angle grain boundaries. Okay, if that to happen, we need to apply very large amount of strains, like a strain, okay, 4 or 6, okay, 4 to 6, true strain of 4 to 6. Then we can see the formation of a very fine grain size having a lot of high angle grain boundary character. So most of the times when you do SPD process, we do see development of a more low angle grain boundaries initially. Okay, more and more low angle boundaries are going to generate. After certain amount of deformation, okay, we do see formation of a fine grains with a high angle character. Okay, so this everything happens with a dislocation based mechanism. All these things are dislocation based mechanisms. Is it clear about the grain refinement mechanism for grain refinement?
Sir, the mechanism on screen is not valid for the processes you showed before this slide, right? Because over here there's a shape change.
Yes, there is a shape change here. Okay, it's not valid. Okay, people have, but it's just GDX. People also giving kind of thing, but it's not okay. People not believing this kind of mechanism. Okay, this can happen. Okay, only under rolling okay, very large amount of strain. If you go for, okay, 99% reduction, if you go for, okay, if you see fine grains in even under rolling, okay, that can be because of this thing. But under SPD, ECAP kind of thing, people actually do not consider this the mechanism. Okay.
So in the rolling, that is before when the sheets are stacked on top of each other.
No, yeah,
That's where you see
without
this
stacking,
mechanism.
without stacking.
Okay.
Okay,
Okay.
simple rolling. Okay, we do
Okay.
see even under okay, but under rolling we do see fine grains as development. Okay, I think in the one of the things also showed there are some fine grains are developing. I think here. Here, see, we do see some very fine grains here in the rolling. Okay, apart from this, okay, elongated grains, we also see some fine grains. Slide number 8. Okay, people have explained formation of these grains by GDRX. Okay, is it clear?
Yes, sir. It is.
This is about the mechanism of grain refinement. Okay, so there are actually 5 basic rules. Okay, for grain refinement. Okay, under SPD process. Okay, the first basic rule. Okay, the deformation has to be done below 0.5 times of melting point. The temperature has to be as low as possible. Lower the temperature, lower the temperature, better the grain refinement we can get it. Okay, that's the first rule. Second one has to apply very large amount of strains to get a homogenized fine grain size. Homogenized fine grain size. Third one, there should be some hydrostatic component. There should be some hydrostatic component. While, okay, if you want to have grain refinement, okay, the process should have the method should induce some hydrostatic component. The fourth one, okay, we need to have, okay, the stacking fault energy play a role. Okay, depending on stacking fault energy, the cell size is going to be different. Accordingly, we do see the difference in the grain refinement. Okay, so I think first one, if you talk about, okay, I think the fifth one, there's another thing, vortex. Okay, we already discussed. We have to induce a vorticity of the metal flow. Okay, so the first one, okay, if you look at here, these are taken directly from this textbook. Okay, these are 5 important steps, rules basically, in order to refine the grain size. Okay, without much shape change in the material. So the first one, we need to have a low temperature. That can then only we can induce very high dislocation density. If the temperature is high, it undergoes easy recovery. Okay, it's not easy to refine the grain size very easily. Okay, but there we talk about DRX, DRV is going to take place. That's a different story. Okay, we need to induce very large dislocation density, which is necessary for formation of a ultra fine grain structure. Okay, similarly, we need to induce very large amount of strain should exceed, okay, 6 to 8, so that we can get homogenized microstructure. Okay, and hydrostatic. Okay, because we need to have finally we need to have a microstructure with high angle grain boundaries. If it is a low angle boundaries, there are a lot of issues. Okay, so we need to have a grains with a high angle grain boundary characters, and hydrostatic component is important. Typically, people apply greater than 1 GPa. Okay, this is basically maintains, okay, solidity. Still, the material will be solid form. Okay, even under high strain, and we also see reduced diffusional activities. The diffusion activity, if there is a diffusion, then we do see a easy recovery kind of thing. We should, okay, control the recovery, the rate of recovery. Then only we can actually induce a fine grain size in the material and suppress the annihilation of deformation induced lattice defects. The hydrostatic component, that's the use of a hydrostatic component. The material vorticity, when it's a vorticity, when you do cross loading, okay, when you change the loading direction, okay, that basically induces a kind of vorticity in the metal flow. So the vorticity can induce, okay, non-monotonous deformation. Okay, the flow in a simple rolling is like a monotonous deformation. Okay, the microstructure change also happens monotonously in one direction. The moment when you change the direction, you are changing the metal flow every time. So that can lead to a, okay, much grain refinement. If you look at here, in case of BC, okay, is more effective for grain refinement as compared to a root C and ECAP method, because the shape change is very limited in C. Only it's 180 every 180 degrees. Here BC, we are changing, okay, 90 degrees every 90, 90, 90 degrees, we are giving more vorticity to the metal flow. The final thing, stacking fault energy. Okay, so depending on stacking fault energy, okay, the grain refinement is going to be different. The amount of grain refinement is going to be different. If I take aluminum and copper, which is going to have a much fine grain size, if I apply same amount of strain, everything same, which of them is going to have fine grain size? Relatively,
Aluminum.
is it aluminum? Why? See, aluminum, I'm talking about high stacking quality material, and copper is a low stacking quality, relatively these two. If a deformed material under speed, same E cap, same root, everything same amount of strain I given, okay, copper is going to see much finer grain size as compared to a aluminum. Okay, the cell size, okay, is bigger in aluminum. Sub cell size and sub grain size, what you are seeing, is going to be higher in a aluminum as compared to a copper. Okay, so by E cap, okay, I can get only 1 micrometer grain size in aluminum, whereas in copper I can get down to 200 nanometers. 200 nanometers I can get it very easily because the cell size is different. Okay, because high stack molecules can recover very fast. Okay, the cell size is because it not cannot reduce the cell size very easily because the recovery is taking place already. Cannot pump in more. We are pumping discharge, but immediately undergoes a recovery. That's why the cell size is bigger in the high stacking field materials. So once your cell size is big, okay, eventually even if whatever grains you're getting fine at the end, it's also a relatively coarse as compared to low stacking fault energy materials. Okay, so these are actually important 5 rules. Okay, one usually apply. Okay, for the grain refinement which is taking place by severe plastic deformation. Okay. So many times people also do cryo rolling, okay, cryo accumulator roll bonding. And I say cryo means deformed metal sub-zero temperature, where you can, okay, aluminum, if I want to get still fine grain size, okay, at room temperature, get okay, 1 micrometer grain size, okay. But if I want to get much fine grain, one has to go to a sub-zero temperature, where recovery can be controlled. If you control the recovery, I can get a finer cell size. That can lead to a finer, okay, grain size at the end of the SPD process. Okay, so these are the things I wanted to discuss. Some important and basic things what we need to know. Okay, because all other methods, okay, whatever methods if you read, all of them revolve around these basic rules in order to get a fine grain size in a material. Okay, is it clear?
Yes, sir. So when we are saying fine grain, are we targeting like nano level grains?
Yeah, so ultra fine because we can get most of the grains, okay, by SPD ultra fine grain size,
Yeah.
okay, between 100 nanometers to 1 micrometer.
Okay.
Okay, so there are actually HPT can induce very large amount of shear strain. Okay, we may get 50 nanometers. Okay, sometimes people also reported some 30 nanometers in some materials. Okay, but most of the times this SPD process can induce ultra fine grain size, a grain size between 100 nanometer to 1 micrometer. Is it clear?
Yes.
Any doubts here? I think so. It's a brief coverage because there's now a lot of things are okay evolving, okay, in this SPD process. So if there's somebody, because this is a textbook which has given, okay, some summary of the book. Now there are several review articles have come after this textbook also. Okay, there are several review articles. So many textbooks have come on SPD process. One of the challenge of the SPD process, scaling up. Okay, all these things were demonstrated in a lab scale specimens, lab scale samples. Scaling is the biggest issue. Okay, so I think in Russia there's a lot of effort going to increase the scalability of the this process. Okay, so Russia they came up with, okay, sheets, even big sheets, okay, can also be subjected to ECAP. Okay, only thing we need to have a bigger, okay, press, high capacity press. There are limitations because we always have some constraints. If you want to do bigger samples, I need to use a bigger dice which can withstand those pressures. Okay, I need to have a press, a huge press I need. Okay, so this is a kind of constraints and challenges, okay, which are basically associated with a severe plastic deformation. Okay, people have very nicely demonstrated grain refinement and a lab scale samples, but the challenge scaling up is the major issue with all these aspirant processes. Okay, so I did not discuss. There's another thing, friction stir processing. Okay? It also induces a grain size, but it uses a concept of okay, DDRX, okay, CDRX concept, dynamic crystallization, where the grain size cannot be much finer. Okay, it will be still coarser in size. Okay, but there still you can get a fine grains, a uniform grain size can be obtained by friction stir process by using a friction and stir the material. Okay, under frictional conditions. So that's a friction stir processing that has come from a friction stir welding. Friction stir welding is known quite a long time. Okay, so we can, without changing the shape, we can apply, okay, apply some friction. So then we apply, okay, and deform the material. So there also we are inducing a metal flow, vorticity in the metal flow that can induce fine grains in the material. So that I did not discuss here, but that's another important thing. But there's a lot of activity happening on friction stir processing of materials. Okay, I hope you got something, okay, from this lecture. Okay, but one lecture is not sufficient to cover one textbook information. Okay? But I taken only an important steps. Okay, if there are any doubts, please let me know. Okay, so I think all of you already saturated. It seems towards the end of the semester.
Sir, in
Yes.
the accumulative roll bonding, there is a high chance of delamination.
Yeah,
So
the
how we,
surface, okay, because every material cannot be roll bonded. Okay,
yes, sir.
there is a
So
limitation. That
how
is a,
we ensure that bonding is going to take place?
yeah, very few materials only people have established. Okay, that accumulate roll bonding. The bonding has to take place. Okay, under rolling conditions.
Yes,
If
sir.
there's no roll bond, then it get laminated very easily. Okay, surface preparation is very important. People do rough surface. They create a rough surface. At least there will be a mechanical keying effect. Okay, mechanical keying, okay, should be there. So at least sometimes metallurgical bonding also develops, only depends on system, what materials, okay, you are talking about. If we talk about aluminum, it gets oxidized very easily. Okay, even if you give some proper treatment, immediately gets oxidized.
Yes,
So
sir.
you
Yes,
cannot
sir.
bond it very easily. Okay, so it is difficult. So people have shown for nickel, okay, copper, those actually can, even at room temperature, at least oxidation is minimum. Okay, so they exhibit very good roll bonding characteristics. Okay? This is because every method will have its challenges. Okay, we have talking general thing, scaling up is a major thing, but even when we talk about individual methods, okay, there are certain issues. Okay,
Yes, sir.
one of roll bonding, the interface bonding is more important. Okay,
Yes, sir.
So what materials basically are being focused or maybe for the ultra fine grain sizes? Is it aluminum or other steel kind of thing is also being targeted?
no, all non-ferrous metals. Okay, nickel, copper, aluminum, okay, titanium alloys, okay, have been, okay, subjected to SPD process very well. Okay,
Why non-ferrous only, sir?
no, because they are actually the strength levels are low. One thing, okay, and the kind of, okay, oxidation problems. If you take a steel, okay, now people are, okay, doing, okay, on stainless steels very easily. Okay, steel ECAP could be done very easily. Okay, but the stress requirement is going to be very high. Okay, for steels, unlike non-ferrous metals. Okay, I need to apply very high hydrostatic pressure for ferrous materials. The capacity of the press are the major problem. Whatever demonstrated, those are actually, okay, done very nicely for all non-ferrous materials, which require very less load requirement.
Okay. And so this,
People in Russia, they have done even for steels also. Okay, they've shown it. Okay,
okay.
but actually, we capacity is a major problem. I think that's okay.
I mean, basically two things. So when we are saying, grain sizes are too small, basically Hall pitch is not going to be applied here, right?
Which
In
Hall?
general, Hall pitch
No,
relation.
yeah, you can apply regular Hall pitch relay. This is a regular Hall pitch because still we're talking 2 nanometers to 1 micrometer. Okay? Regular. We may see some little bit deviation.
Uh-huh.
I think if I see my one of the lectures, okay, there I
Yeah,
mentioned there is a deviation below 1
yeah.
micrometer. Okay.
Inverse Hall pitch, yes, sir.
Yeah. No, inverse Hall pitch comes below 20 nanometers. Okay, typically.
Okay. Uh-huh.
There is some deviation. The slope, initially we have some slope, there will be some deviation followed by a inverse Hall pitch.
Because, sir, in general for nickel, like we see there is something called strong coupling and weak coupling. As the sizes go on reducing,
Mhm.
I don't remember what was the this threshold size where this weak coupling starts, so that strength goes not down actually in spite of increasing with the grain size.
Mhm.
But anyway, I mean overall we can say that this is these are the methods to get ultra fine grain sizes.
Yes, you are right.
So, thank you.
This is a top-down approach. Okay, all these things are top-down approach. Okay? Fine grains can be obtained by two different routes: top-down approach and bottom-up approach. What okay, SPD process come in the category of top-down approach. We take a already solid material and refine the microstructure internally.
Got it. Thank you, sir.
Yeah, thank you. So, any more doubts? Clear? Then I'll stop recording. Okay. So we have one more lecture. So we'll meet on Friday. Okay. Happy Diwali to all of
Happy
you.
Diwali, sir.
Happy Diwali. Thank you.
Happy Diwali, sir.